Hello, I am Jeff Warren Jr., Assistant Editor for the Facilities Market of Trade Press Media Group. Thank you for joining today's webcast, Strategic Water Management, Ensuring Quality and Compliance in Domestic Systems. Thank you to our sponsor, Hans Premium Water, for helping to make today's webcast possible. Our presenter today is James Dipping. James is the Principal Operations and Discipline Leader, Plumbing Engineering with Stantec. James specializes in healthcare and mission-critical facilities. His main responsibilities include training development, engineering standardization, specification maintenance, design programming, project management, team leadership, and quality control. Today's webcast learning objectives include understanding key factors involved in evaluating water supply and quality for premise domestic water systems, exploring various treatment options for maintaining high water quality standards in domestic water systems, learning proactive maintenance strategies to ensure the reliability and safety of water systems, thereby enhancing occupant well-being and satisfaction, and comprehending the importance of exceeding regulatory standards to achieve stakeholder satisfaction and ensure regulatory compliance in water quality management. Before we get started with today's event, I'd like to cover a few housekeeping details. We do encourage audience questions throughout the webcast. To submit questions, please navigate to the Q&A button at the bottom of the screen and type in your questions at any time. At the conclusion of today's webcast, you will receive a PDF copy of today's presentation slides. You will also receive a link to take a brief online assessment. Upon successful completion of this assessment, you'll receive your CEU certificate. Today's webcast will also be archived at facilitiesnet.com/webcasts. Now I will pass it over to James.
All right, thank you, Jeff, and good afternoon, everyone attending. My name is James Dipping, as previously mentioned. Today we're going to talk about water management, strategic water management, and ensuring the quality and compliance in domestic systems. I'll be turning my video off just to save bandwidth, and we will get started. So as Jeff alluded to, the agenda today is understanding water quality, and we're going to talk about the effects that poor water quality can have on domestic water systems. We're going to look at some water treatment considerations. We're going to look at waterborne pathogens and Legionella in domestic water systems. We're going to discuss occupant well-being, and then we're going to look at water management plans and how we can utilize water management plans to improve the health and safety of the occupants in the building. So the first topic is understanding water quality and effects of poor water quality issues. So one of the most important things that anybody who's in facilities or myself who's a design engineer needs to understand is that water quality and the water that comes from the municipality varies considerably from one city, one location, one county, from one city to the next. So there is a very inconsistent way to even understand what the quality of the water is that comes into the building. When we talk about water quality, we're really talking about what is the disinfectant used, what is its turbidity, its pH, total organic compounds, hardness level, total suspended solids, amongst many other things. So when we talk about how it varies from one location to the next and all of the different factors associated with kind of trying to understand what water quality is, there really is not a one-stop shop when it comes to solving water quality issues. Water quality delivered to a building is extremely unpredictable. It changes by location and even by season in many locations. So when we talk about water quality and what effects it could have on a domestic water system, this slide is kind of intended to talk about what poor water quality and how detrimental it could be to the operation and functionality of a plumbing system. It's estimated that for every 1 grain of gallon of water hardness, water heater efficiency, that's the transfer of heat from a fuel source into the water, is reduced by 4%. Scale can also build up in piping system, most notably galvanized steel. And we'll talk about what water quality factors contribute most to the scale buildup in later slides. The scale development can increase pressure losses, reduce flow, and can create an environment for biofilm growth and thus bacteria development. The answer is not as simple as adding more disinfectant. So what is disinfectant? What is disinfectant residual? Disinfectant is going to be the tool that a municipality uses or potentially a building uses to try to kill bacteria or other waterborne pathogens, viruses, things like that, that might come into the building via the water supply. And if you have problems, the answer is not always as simple as adding more disinfectant. Excessive amounts of certain disinfectants, such as chlorine, in a water system can lead to the creation of disinfectant byproducts. These byproducts can be potential carcinogens to humans. Byproducts are created when chlorine or chloramines or other oxidizing disinfectants, such as monochloramines, mix with organic matter in the drinking water supply. Think, bits of dead leaves, ground up sticks or whatever might have made it through the water filtration and the municipality's water purification plant, and suspended solids in the water. And that's where these disinfectant byproducts are created. So one of the water quality metrics that we talked about earlier was turbidity. So what is turbidity? Turbidity is a measure of the cloudiness of water. Turbidity is used to indicate water quality and filtration effectiveness. Higher turbidity levels are often associated with the potential of higher levels of disease-causing microorganisms, such as viruses, parasites, and some bacteria. These organisms can cause symptoms such as nausea, cramps, diarrhea, and associated headaches. Another important factor in water quality is the pH, or the alkalinity or acidity of water. The reason why this factor is so important is because many of the disinfectants that are put into the water by the municipality could be greatly affected by the pH of the water. Chlorine, as a matter of fact, is very strongly influenced by the pH of water. Anything that has high pH values, anything greater than 7.8, lead to the formation of hyperchlorite ions, which do not have any biocidal efficacy, but are corrosive to materials at the construction of the plumbing system. So what that's trying to say is, if your water is acidic, meaning that the pH is greater than 7.8, it's going to basically negate the effectiveness of chlorine, and then it's actually going to become very corrosive to the metallics in your plumbing system. Chlorine dioxide, which is another disinfectant option, is relatively unaffected by pH. Monochloramines, the effectiveness of monochloramines is not necessarily impacted by the levels of pH in drinking water, because it's a much different and highly stable chemical compound. And then if anybody's familiar with copper silver ions, that disinfectant tool, which is typically applied inside of buildings, can be affected if the pH gets to be too high. So knowing what the pH of the water is in your building and being able to select the right tool and knowing how it affects the disinfectant is very important. So now we're looking at total suspended solids. So total suspended solids is the weight of solids remaining after a well-mixed sample is filtered through a standard glass filter, and the suspended portion is dried to a constant weight at 103 to 105 degrees Celsius. Total suspended solids are essentially food for future scale and biofilm development. Consider filtration as a means to starve a domestic water system and reduce the development of scale and biofilm by reducing the amount of total suspended solids in your system. Total suspended solids can cause disinfectant and other plumbing components to not operate effectively, because they can block the access of the disinfectant to the source that it's trying to work on, and can cause a lot of scale buildup in the plumbing system. Water hardness is probably something that a lot of us are very familiar with. Water hardness is the amount of dissolved calcium and magnesium in water. High levels of hardness can cause scale to grow, and the Water Quality Association estimates that, as we talked about earlier, every grain of hardness, or every 5 grains of hardness per gallon of water, can create a 4% loss of efficiency and a 4% increase in the cost of energy in gas storage tank water heaters for every 50 gallons of hot water used a day. So scale and water hardness has a significant impact on the performance and the health of the water in your building. There's a lot of anti-scaling treatment devices aimed to reduce, prevent certain scale deposits that are normal to hard water behavior. This includes technologies such as physical water treatment devices, as well as sacrificial media. These technologies may provide a measurable reduction in hardness depending on the measurement method applied by conversion of calcium and magnesium ions to a precipitate form, but do not provide a reduction of total calcium and magnesium content of the treated system and are not proven to achieve hot water. I myself have been approached by a lot of vendors who have talked about anti-scaling technologies and things that you can do to your water to try to reduce the hardness, so to speak. But as we just talked about, those really are just turning them into a precipitate, not taking them out of the water. So what do we do and how do we treat these different varying water quality concerns that we've just talked about? The first one is very simple. It's just filtration. So when do we want to employ filtration? When the incoming water supply has high levels of total suspended solids, think 1 to 10 microns, filtration should be installed upstream of plumbing appurtenances and softeners and booster pumps if incoming pressure conditions allow. What does incoming pressure conditions allow mean? There's always going to be a pressure drop through your plumbing equipment, especially a filter, when you're trying to push water through something that's trying to capture particles out of it. So you might have, for example, a pressure drop of 10 to 15 pounds per square inch at a given flow rate. What we're trying to make sure is that if you have a booster pump or a softener upstream of it or any other piece of equipment, you take that pressure drop into account as part of your overall domestic system design. So by reducing suspended solids, the result is a lower organic demand for disinfectant, reduced biofilm growth potential, reduced potential for deposition, and reduced maintenance and requirements for plumbing components by eliminating or reducing particulates that can cause erosion or deposition on plumbing components. Just like we talked about earlier, removing this total suspended solids is removing the food that helps produce scale and biofilm development. Carbon filters work by design by removing all oxidizing disinfectant. They're very popular at a point of use for a coffee filter or a water dispenser. They take the chlorine out of the water, but they can also remove organics and metals, including lead. Another treatment option is water softening. Water softening should be selected based on the application. So what you really need to know and what you really need to do is talk to your water purveyor and understand what the water hardness is. A lot of this information is available online from the water purveyor where you get your water delivered to your building from. So anywhere from 0 to 3 grains per gallon, and the conversion is very simple from grains per gallon into milligrams per liter or parts per million. Milligrams per liter and parts per million are the same thing. You take the grains per gallon, multiply by 17.1, and that's where you get your parts per million or milligrams per liter. So anywhere from 0 to 3 grains per gallon is soft water. You really shouldn't have to do any treatment. 3 to 7, moderately hard water. You might want to consider treatment for domestic hot water systems. And the reason being is much like what we talked about with the technologies used to essentially reduce hardness that aren't water softeners, because water softening is an ion exchange. The technologies that we talked about earlier are really just turning the calcium and magnesium into a precipitate. And that's what's going to happen that also happens when you heat hot water. A lot of that capacity to hold calcium and magnesium lessens when the water temperature goes up. So, when you get to that 3 to 7 grains per gallon, you really want to consider maybe softening for your hot water systems. Anywhere when you're 7 to 10, you might want to look at it for the incoming cold water, depending on the end use applications. And what that means is, if you have equipment or something that's being fed, as opposed to maybe just somebody taking, a shower, washing their hands, flushing toilets, you might want to consider a point of entry water softening system. And then when you're looking at 10 grains per gallon or anywhere north of 171, 175 parts per million, water softening should be considered for the entire system. Now we're going to talk about supplemental disinfection. Supplemental disinfection should be considered based on the following. And this is where we kind of talk about, we'll talk more about this when we get into water management plans. And we'll also talk more about this when we look at the Legionella side of water quality and how all of these different tools affect the development of Legionella in a domestic water system. Supplemental disinfectant should be considered based on the building's population risk. So if anybody's familiar with ASHRAE 188, that tool and that standard will define some of the buildings where a water management plan should be considered. This should be considered based on what the primary or secondary disinfectants, namely chlorine and chloramine in the water from the water purveyor, what their levels are and how effective they are when they get to your building. And then the plumbing engineer will need to work with the local purveyor as well as the required municipal environmental protection agency, because anytime you implement a supplemental disinfection system, you're essentially altering the quality of the water in the building, adding something to it, so to speak, as opposed to just taking something out. And most municipal environmental protection agencies want to be able to be aware of what's going on and approve of what's going on. And one thing to note that we use the term supplemental instead of primary and secondary disinfectants, because the primary and secondary disinfectants are what's typically used at the municipality level. Supplemental is what's used at the building level. So supplemental disinfection can start with chemical disinfectants that can be found in the building water system when the incoming disinfectant levels in the water supplied by the public water utility are insufficient. The most three popular chemical disinfectants that you're going to find and are also listed in the United States Environmental Protection Agency are going to be chlorine, chlorine dioxide, and monochloramines. I myself have a lot of familiarity with chlorine dioxide and monochloramines as a tool for supplemental disinfection at the building level. And as we talked about earlier, all disinfectants applied to potable water must be EPA FIF-RA listed and approved to the ANSI NSF standard 60 and 61 for potable water use, again, because they're altering the basically the chemistry of the water coming into the building. So kind of specifically focusing on chlorine. Chlorine is one of the most common supplemental disinfectants due to its low cost. Chlorine can be used to treat hot water, cold water, or both. If it's fed into the cold water supply, most of the free chlorine will typically be consumed in the water heaters with any storage capacity. And like I was saying earlier, a lot of the disinfectants and the temperature change in heating out water has a pretty dramatic effect on how well primary and secondary disinfectants work, and a lot of supplemental disinfectants work, along with changing the chemistry of the water based on having precipitate from a lot of different things such as the water hardness and things like that. So due to its high oxidant reduction potential, which basically means its killing effectiveness of bacteria and viruses, chlorine decays quickly in hot water, which makes it difficult to establish consistent residual. And residual means life length, like how long it's going to last from the time you put it in the water to when it becomes non-existent anymore. So the larger your building is, or the more complex your plumbing system is, really it needs to be taken into consideration as to how you want to use chlorine as a supplemental disinfectant. So due to its high reactivity, also chlorine does not penetrate the biofilm. So if you have a situation where you have pre-existing biofilm in your plumbing system, chlorine is not really going to be the tool that you want to use to try to mitigate any waterborne pathogen or get rid of biofilm. It's just highly reactive, and it gets eaten up by the water and stuff that's floating in the water before it ever really gets to biofilm. And the other issue is that chlorine reacts with natural organic matter, and it can potentially form disinfection byproducts. We talked about those earlier. One of them is a trihalomethane, and some of the other ones haloacidic acids, and then those are regulated under the EPA. Disinfection byproducts have been linked to cancer, especially bladder cancer, but also to interfere with the proper function of the liver, kidneys, central nervous system, and reproductive system. As a result, utilities making use of chlorine and chloramine need to balance the risk of pathogenic microorganisms that must be eliminated against the potential longer-term risks to the public health from these disinfectant byproducts. The EPA has identified several byproducts, such as what we just talked about, where maximum levels must be maintained or are listed as carcinogens. Another carcinogen or another byproduct, disinfection byproduct, is going to be called cyanogen chloride. This is a disinfectant byproduct of chloramine that is currently not regulated by the EPA. Cyanogen chloride is a highly volatile and toxic chemical asphyxiant that interferes with the body's ability to use oxygen. Exposure to CK can be rapidly fatal. CK is used in tear gas, in fumigant gases, and as a reagent in the synthesis of other compounds. So, as you can understand, you have to be very careful and very selective because there's good and bad that can come out of any choice that you make. Another treatment option is going to be chlorine dioxide. Used as a primary municipal water disinfectant for multiple purposes, including a reduction of the formation of trihalomethanes and controlling algae odor and manganese. Chlorine dioxide has disinfection properties second only to that of ozone among the commonly used disinfectants. Chlorine dioxide has actually become more common to use than straight chlorine as a primary and secondary disinfectant in many municipalities. Chlorine dioxide can be fed into the building water system from aqueous solutions with concentrations of about 175 grains per gallon that can be generated on site. Peer-reviewed studies in the scientific literature reported that the use of chlorine dioxide can increase the corrosion rates of metallic components in plumbing systems and can embrittle plastic components, including plastic pipes. Another thing to consider about chlorine dioxide is that when it's generated on site, some of the chemicals that are used in the equipment that generates chlorine dioxide could be explosive. So usually a dedicated room has to be set aside in the facility when chlorine dioxide is implemented, and emergency showering equipment also has to be provided because the chemicals, according to their MSDS sheets, require showering or eye wash or both. And the room, it requires its own dedicated room. It can't be just laid empty and open in a mechanical room. So one of the last chemical option is going to be a monochloramine. Monochloramine is commonly referred to as chloramine or chloramines and is widely used as a secondary, like a distribution line disinfectant by many public water systems. Monochloramine is significantly more stable than other oxidizing disinfectants. We're talking the chlorine dioxide and the chlorine that we just talked about. And because of that, it's easier to establish consistent residual through the building plumbing system. By it being more stable, it also is not as affected by temperature. The residual means it will persist in an uncirculated leg pipe much longer than chlorine or chlorine dioxide. It can fully penetrate the biofilm and reacts less with the organic matter in the water, therefore by producing fewer disinfection byproducts. And then the monochloramine decay leads to the formation of free ammonia. The formation of free ammonia is mainly influenced by water temperature and water age. Although free ammonia is not a regulated contaminant under the Safe Drinking Water Act, monitoring it is advised, as elevated levels of free ammonia can increase corrosion rates for copper piping and building systems over the long term. So monochloramine is, I don't want to say a relatively new technology, but certainly out of the three chemical options that we've discussed today, one of the most is the most stable and has the best potential for protection of the plumbing system and effectiveness as a biocide. A non-chemical option for water treatment and essentially bacteria treatment is copper silver ionization. Copper silver ionization is not listed as a disinfectant under the Safe Drinking Water Act. but it has been widely used in building domestic hot water plumbing systems for Legionella control. Copper silver systems use copper and silver alloy bars that are release positively charged metallic cations into drinking water by means of electric current. You see here in this picture that there's flow cells that have power generated to them, and that positive charge that we just talked about is what allows the copper and silver bars to release ions into the water stream as it flows through the flow cells. So the stability of copper silver ions is not significantly influenced by water temperature, but it could be affected by pH if not managed appropriately, as we had talked about earlier. Copper silver ions do not react with organic matter and do not produce any disinfection byproducts. The concentration needs to be shown as in this slide. And one of the good things about copper silver is it doesn't require any special rooms. It doesn't require any emergency plumbing fixtures. It's a very simple, safe, and effective way to mitigate the risk of waterborne pathogen development in a plumbing system. Ancient times have used copper and silver as a disinfectant method for many years. I'm sure you can go to a Walgreens and see copper and silver inputted into many athletic gear and other tools as a tool, for helping with disinfection. These same principles are being applied with copper silver ionization in the domestic water system. So now let's talk about Legionella and what kind of causes Legionella to grow in the system. Legionella basics. Legionella is found naturally in freshwater environments like lakes and streams, but generally in low amounts that do not lead to disease. Legionella typically becomes a health problem in building water systems. And in order to become a health risk, Legionella has to grow or multiply, and then it has to be aerosolized so that people can breathe in the small contaminated water droplets. It doesn't affect you if you drink it. It only affects you if you breathe it into your lungs. So there are numerous ways that Legionella can be transmitted to and infect humans. It is generally accepted that it's breathed in, as we just talked about. Now, I said you can drink water and not get Legionella, but the caveat to that is if you cough or aspirate while you're drinking water containing Legionella, if you vomit or have any other way of introducing the Legionella contaminated water into your lungs, you can still get Legionella that way. And only Legionella is typically not transmitted from person to person. It's only been reported once, and Legionella is often diagnosed 10 to 15,000 times a year. So you typically don't have to worry about contracting Legionella from somebody who already has it. So how are these droplets formed? So a variety of devices can produce aerosols containing Legionella in droplets of respirable size. Sink faucets, shower heads are a very, very common application. Cooling towers, in fact, the first case in the discovery of Legionella was from American Legion in Philadelphia in 1976. And Legionella was in the water, and the plume from the cooling tower affected hundreds of people, which is what spawned the discovery of disease. Evaporative condensers, decorative fountains are very common. Whirlpool spas, humidifiers, misters. I was just in Utah in the desert, and there was misters all over the place. So misters, you breathe in that air with the mist in it. If that has Legionella, that's going right to your lungs. And then respiratory therapy equipment filled with tap water, dental unit water lines. They splash all that water around inside your mouth when they're cleaning your teeth. That's, warm, relatively low flow water that could have Legionella in it. You breathe that in, you cough a little bit, that gets into your lungs. So outbreaks of Legionellosis from whirlpool spas have occurred among both bathers and non-bathers, and then data from a few outbreaks attributed to cooling towers suggest that Legionella contaminated drift might be often carried beyond the building site itself. So the factors that lead to Legionnaire's disease is the entry, the disinfectant residual being poor, water supply disruptions. Once it's in your building, it's growth. So the factors that affect growth are going to be temperature, that disinfectant residual, system design, the sediment that we talked about, the total suspended solids, the hardness, the scale, the biofilm, the nutrients, and microbial associations, the transmission, meaning that it's got to get from the plumbing system to the person. So aerosol production, distance from the source, temperature of the water, again, humidity in the air can help these droplets last longer in the air, not dry up. Exposure to susceptible humans. So some of the factors that we're not necessarily getting into in a depth level with this presentation is going to be the person themselves. What is their age? Do they have any pre-existing conditions like disease or immunodeficiency? And then when all of that is put together, you can have somebody who potentially gets Legionnaire's disease. So temperature obviously is very important too. So when you're talking about the operation of your plumbing systems, you want to make sure you're kind of steering clear of the optimal growth range, as kind of indicated here in this temperature guide provided by the ASHRAE Guideline 12, which will also be found in the Uniform Plumbing Code in Appendix N. So let's talk about occupant well-being, right? We're talking with people who operate facilities, and their concern is making sure that the occupants in their building are safe. So waterborne pathogens, again, we're going to talk about Legionella. We talked about the 4 major contributing factors, which is water temperature, water quality. We talked about all the different factors that go into water quality. Water age. Water age is the term that's used to define how long has the water been in your building since it got in from the water source. And disinfectant residual. Water age and is linked to temperature and disinfectant residual because water can come into your building cold and it can warm up based on the ambient surrounding temperature of the plumbing chases, the rooms, and everything that the water has to pass through to get from the point of entry to where it's used. And with that time frame is also the residual. Well, we talked about the chemical disinfectants that have a residual. Chlorine has a very short residual. It might only be good for a couple of days from when you get it from the municipality, all the way up to monochloramines, which might last a little bit longer. But again, it doesn't last forever. So any dead leg that sits for a couple of days, a week, more than a week, you're really looking at a high potential for Legionella. Cold water has gone from cold to warm. Hot water has gone from hot to warm. It's going to pass through and be in that ballpark of that Legionella growth temperature range. And that's where a lot of these factors and how these factors come into play with the development of Legionella. So, we just talked about temperature, aerating, distal sites, plumbing fixture selection. So as a design engineer or facility manager, take a look at the fixtures that are in your building. Plumbing fixture selection not only can impact the flow of water in a building, the emphasis that we've had with a lot of the third-party green building grading systems now for low flow has actually had a very detrimental effect to water age. And we're finding that low flow is not the answer when it comes to how to help mitigate the development of Legionella in a system. As we talked about earlier, water age increases, oxidizing disinfectant from water purveyors dissipate or are consumed in the disinfecting process. Flushing should be considered when we're talking about lakes that haven't been used for a long time, rooms that are left unoccupied. Get rid of the old water, bring in the fresh water that has a higher residual level of disinfectant. And then water quality and nutrients. The incoming water in and of itself, as we talked about earlier, has the potential to contain nutrients and bacteria and biofilm that will be a food source for everything that we've been talking about. So water management plans, and we'll talk about what they are and how they can become very, very effective in helping maintain and understand what your domestic water system is doing and how you can take the corrective actions in case something becomes amiss. So the first step in a water management plan is kind of knowing what your building is and knowing who's in it. Is anybody immune compromised? Is anybody of the elderly or very young demographic? Are you in a healthcare facility that has an ICU, a NICU, a cancer center treatment? Are you legally susceptible to litigation? Like, are you an apartment building, a hotel, or other housing type where the occupancy fluctuates and there's potential that the occupants are not healthy? I mean, if you're in a hospitality environment, you have no control over who comes in and who leaves your building. You don't know if they're healthy, you don't know if they're young, you don't know if they're old, you don't know anything about them. You just know that they're using the water in your building, and you have to know and be of the utmost concern that your building is providing the healthiest possible water it can. So there's a methodology to this. A water management program is a multi-step process. Every building is different and needs a tailored program. So the first thing is find the right team members with the right skill sets and expertise. The next step would be describe the building water system using a flow diagram like what you see on the right, and what we'll actually see in a couple of slides, and a written description. In other words, illustrate the path of water from start to finish in your building. And identify areas where Legionella can grow and spread. We talked about the fixtures, we talked about the processes, we talked about the people that can have susceptibility to Legionella. So know how water gets to those showers, to those water fountains, to those cooling towers, and to those other low use areas in the building. So who's on the team? Consider among your employees, your partners, your outside experts who can provide the skills so that you can develop the most effective program possible. It's gonna be yourself, the building manager, the building administrator, the maintenance or engineering employees. You're gonna have safety officers. You might have a chemical supplier that works to provide corrosion inhibition for your cooling tower. Obviously, the building owner is going to want to be very involved in this process. You might hire an engineer to help you understand what processes are being done to your water, and then what volume of water you're looking at in your piping network. You might have a microbiologist, you might have somebody on your team who helps you test and understand where you need to test and what control points you need to establish. So when you're developing it, this is that flow diagram that we were talking about. And a lot of these pictures that we're looking at here are taken from the Centers for Disease Control. They have a water management plan toolkit, okay? It does one step further than what the ASHRAE 188 standard does. The ASHRAE 188 standard kind of defines what needs to be done. The CDC toolkit kind of outlines the specific steps to getting from start to finish in a water management plan. So this is the flow diagram that we were kind of talking about. In this example, we have a building with a 4-inch pipe from Maple Street. It splits, it goes to fire protection, and it starts delivering water to the fixtures in the building. In this case, we have a cooling tower, we have a decorative fountain. Ice machines are another common source of Legionella, especially in healthcare applications, because the water supply that goes into the ice machine is often on the backside of the ice machine, where all the heat rejection is from the refrigeration process. You've got sinks and showers, you've got hot tubs, you've got pools. Okay, you've kind of got the whole gamut of things that we talked about in this building. The water is heated in the basement, the water is heated in the kitchen. So we got a lot of different processes going on. That hot water is then delivered to sinks and showers, and then ultimately it all goes to the sanitary sewer. You don't really need to get into a very, very detailed understanding of your plumbing system, except maybe when you're looking at a flushing protocol. But when you're really talking about understanding where your temperature issues could be, your stagnation issues could be, where you might not have any disinfectant, or you have an aerosolization location, that's where this slide has come in. It's taken that same slide we just looked at. It's looked at on a more detailed level. Okay, I might not have any disinfectant anymore at my showers, my hot tub, my cooling tower, and my decorative fountain. Understanding that the disinfectant that I get from my municipality has dissipated. What do I need to do? Because I know right now I'm not doing any supplemental disinfection myself. And then the list on the left is to kind of talk about the different tools that are in your building, storage tanks, water hammer arresters, filters, things like that, where a sediment can build up or you have a large volume of water sitting. So flow rate through it or stagnation is a little bit higher than a typical pipe, things of that nature to understand, your areas of concern. And then this is basically saying what are at risk, and then knowing where at-risk occupants are in this also. So if you were in a healthcare situation, again, knowing that I have an ICU on the 7th floor of my building, that's going to be a understanding that, okay, we've got to make sure that we're doing the right thing in the water supply, feeding the 7th floor, and then with the fixture selection at the 7th floor. So now we get into the execution, and the execution is going to be largely dependent on control measures and implementation and monitoring. So the diagram here kind of talks about what you do when you've identified what a control measure is. And so a control measure is going to be looking at, say, this diagram and saying, okay, I want to make sure that I've got the right temperature in my distribution. I'm going to check my delivery temperature at the water heater, as you can see here in this diagram with the green temperature gauge at the water heater. And then I want to check it as it flows through the building to my fixtures. So this process is kind of what do I do when I set my control limits? What temperatures am I looking for? What range of temperatures am I looking for? I'm going to go around and document them. I'm going to go around and test for them. And then I'm going to have a process for what do I do if the temperature is too high? What do I do if the temperature is too low? And take that corrective action, document it, and then follow up to make sure that your system is operating accordingly. So what you'll see here on the right side in yellow illustrates the routine process of monitoring control measures to make sure they are within limits. And then on the left side in orange shows the process of what to do if the control measures are found to be outside the limits. So you kind of take an action, a corrective action, document the remote, see that you go back into within limits. Yes, you're kind of back into your yellow loop. If you find that you're not within your limits, you're going to keep making adjustments to your system, documenting what those adjustments are as part of the process, and then repeating steps in a logical manner to get back to within your control point. The execution of water management plans is also going to be largely dependent on your team, and it's going to be largely dependent on control measure implementation and monitoring. So examples of chemical and physical control measures, water quality should be measured throughout the system to ensure that the changes may lead to Legionella growth, such as a drop in chlorine level, are not occurring. So check disinfectant levels, and you can see here in this particular diagram that we have on the right, you're checking disinfectant levels at many different locations where the previous slide indicated we didn't have any disinfection. You want to check it at the main source to understand that what you're getting in is consistent. It's not changing. You don't need to make any adjustments to whatever supplemental disinfection you might be employing inside your building, but know that you want to check it at the cooling tower for the reasons that we talked about: decorative fountains, sinks, showers, and hot tubs. Water heaters should be maintained at appropriate temperatures. We talked about how important water temperature is to, one, the mitigation of Legionella as a simply disinfectant property from temperature, but also how temperature affects chlorine, how temperature affects chlorine dioxide, how temperature affects hardness precipitation in the water system. So there are a lot of different reasons why being consistent with water temperature is very, very important. Decorative fountains should be kept free of debris and visible biofilm. Clean the things that you can clean. A decorative fountain that has algae growing inside of it, it might be getting clean water from a delivery standpoint, but keeping that water or keeping the surfaces in there clean, biofilm free, things of that nature is obviously very important. And then disinfectant and other chemical levels in cooling towers and hot tubs should be continuously maintained and regularly monitored. You're going to work with the partners that you've established as part of your water management team to make sure that you have the data that proves that you're within your control measures, you're monitoring them, and then you've taken any correction action necessary. So kind of to summarize, what we're talking about today is water quality is going to vary rapidly across our country. Water quality plays a critical role in building performance. There is no one-stop shop in treating water. We can see there's a lot of different, things that go into good water quality, and there's a lot of different ways that you can manipulate the turbidity or the total suspended solids or the disinfectant, so on and so forth, with different ways of treating water. So the water quality we talked about, disinfectant is going to be different. Water temperature is going to change. Water age is going to change. And that can change seasonally. Disinfectant is going to change seasonally. If it's warm, in the summer and it's cold in the winter, the disinfectant that the municipality puts in might not be as high in the summer as it is in the winter. Obviously, the water temperature is going to be warmer in the summer than it is in the winter. I'm in the Chicago area and I can see water temperature swings anywhere from 38 degrees in February or early March, all the way to this time of year, we're going to be close to 70 degrees. And then water age. People use more water in the summertime with all of the irrigation and at least in my area, with the irrigation and cooling processes that are water dependent. So testing and determining the incoming water quality to your facility is imperative, and you need to do this consistently. And then lastly, understanding how to manage water in your building is key to occupant health and safety. So I think with that, Jeff, I'll see if we have any questions that that might have come up during the presentation.
All right, so we'll start the Q&A. First one is can you tell me what would be an adequate amount of time to flush pipes in a petty harmonic unit with unoccupied rooms on the 7th floor prior to placing a patient in the room?
Well, what I'll kind of, I don't want to say skip over the room type, but what I'll say is this: the time it takes to flush water depends on the size of the piping network and the length of the piping network that supplies that room. So for example, let's take a 10-foot long, a 3/4 inch pipe that has about a half a gallon of water in it. If that water's been sitting for a couple of days, you want to flow and clean. Let's say you want to clean that 10-foot length of pipe out that has a half a gallon in it. You have a half a gallon GPM aerator on your fixture. You're going to flow that fixture for 1 minute. Okay, if you had a 1 gallon per GPM aerator on it, you'd flow it for 30 seconds. So this is where I was talking about earlier. The engineer would help you understand what that time duration is. I hope that answers the question.
All right, and what are your thoughts about reverse osmosis water filtration systems?
So I think reverse osmosis water filtration systems are great. They have a lot of different applications. They consume a lot of energy. As far as filtering out a lot of the things that we talked about, I think they can go a long way. But I think you want to put things upstream of them in order to reduce the maintenance of the actual membrane itself. Reverse osmosis can actually filter out things down to viruses and bacteria very effectively. If you looked at point of use, if you have a Legionella outbreak and you looked at point of use filtration that some companies sell, they're actually selling you RO filters at the point of use. Again, they're energy hogs. They're very, very expensive, but they're very, very good at what they do. And when you are done with an RO filtration system, you're gonna have very good water that I don't want to say is overkill for a lot of standard domestic water applications, but they're a lot maybe less expensive and less maintenance involved ways to treat the water and keep the system clean.
All right. And how often should you flush pipes that are dead legs?
I like to kind of look at the 2 to 3 day ballpark. If I have water that's been sitting for 3 days over a weekend, something like that, like flushing would be something that I'd strongly consider at that time frame.
What is the target value of hardness at building level?
I'd say if we were to go back and look at that slide, you want to be at that about 5 to 7 grains per gallon of hardness, I'd say for a target. And then you want to look at the applications downstream and see if anything requires a lower value of hardness. I've worked in a lot of medical applications where sterilization equipment has very low water hardness requirements where you might put in a point of use softener at that point, but typical plumbing systems, I'd say 5 to 7 grains of hardness is a good target.
All right. And as a building manager or operator, what are some immediate steps you can take to improve the domestic water quality in your building?
So immediate steps I would take are, that initial testing, knowing what the water is coming into your building and see, what steps do I have to take? What metrics do I care about? What steps do I have to take if I'm exceeding or not meeting those metrics? If I have a high level of total suspended solids, like I said, I really want to start looking at maybe a filtration system because now we're talking about all of the possibilities of food, scale, and biofilm growth that can happen down right, immediately inside the building and throughout my entire plumbing system. Do I have enough residual of disinfectant? If I don't, then I really want to start looking at, okay, I need to get my disinfectant up in my building and get it to a point where I'm in control of this and not, proliferating the development of waterborne pathogens. So I think knowing the first step is knowing what's coming in your building from a water quality standpoint. That's beyond paramount. After that, taking the steps to address the issues is extremely important.
All right. And if there is a renovation planned in your building, what things should you be on the lookout for during design or construction of the renovation?
So um, if I'm looking at a renovation and I'm a building, this is my building to manage, and there's a renovation happening in my building, I'm looking at a lot of different things. What materials are being used? We kind of talked about this a little bit in this presentation, but galvanized steel is pretty well documented these days, and I've seen it in my own experience quite a lot, to be a very, very susceptible to scale and biofilm development. So it's a much less, it's a cheaper material to use compared to like a copper or stainless steel, but it comes with other factors that you need to consider from a design and construction standpoint. I'd want to look at, valves and locations of valves and serviceability of a system and the ability for me to flush water. I'd want to look at, are there mixing valves at, sinks and fixtures that are going to alter the water coming out. Now, we all understand that there's going to be situations where code is going to mandate them and we can't get around that, but it'd be nice to know what that is and where they are. I'd want to look at any other water treatment processes that might affect, are they generating their own hot water as opposed to using base building hot water? If they are, what are the set points for that? How is their system operating? Is it set to shut down over the weekend for energy saving applications? So there's a lot of different things I think you can look at: materials, the operation of the system, the size of the system. Do we see a lot of oversized piping in there that would increase water age, increase surface area for scale and biofilm development, things of that nature?
Are there standards for what fixtures should be supplied softened water?
From a plumbing fixture standpoint, no. Most of the softened water requirements that I see come from manufacturers of equipment, whether that be food processing or cooking equipment, or sterilization equipment, or humidification equipment, those have standards. General plumbing fixtures do not. But what you'll see is that they obviously have scale buildup, not only inside the fixture itself, outside the fixture as well. But anytime you get into an application where cooking, sterilization, or humidification are at play, softened water is something that you should be very, very well aware of. And the hardness of your water coming into your building and going to those applications is very important.
All right, I believe that wraps up the questions. There is one. Can we reach the presenter with questions after the presentation?
I have no problem with that.
All right. Well, I believe that should wrap up the Q&A. Thanks, James, for the great presentation today, and thank you everyone for attending our event today. One final reminder, this event was recorded and will be archived on facilitiesnet.com. And if you would like to get a CEU for attending today's event, watch your email for a link to take our CEU quiz. Once again, we appreciate everyone being here today. This will conclude our webcast.